earth am I?
You're in an uranium mine in Colorado.
Why is it so dark? Am I blind?
Oh, I'm so sorry. How careless of me. Is this better? On the surface of the nucleus of a common uranium atom.
Sparkling shekels. Why, I recognize you from Professor Igor's lecture. You're Professor Ernest Rutherford.
Rutherford, at your service. Pleased to meet you, Mr. Tompkins.
How do you know my name?
Oh, I've delighted in all your adventures, Mr. Tompkins, in the series of books written by George Gamow, the father of Professor Igor. In some circles, you really are quite famous.
Me? Famous? What do they say about me? Do all the ladies like to...
Come, Mr. Tompkins, we don't have all night. You're on the verge of waking up, so you'd better ask me any questions you may have very quickly.
So, if we are standing on the surface of a uranium atom's nucleus, then I presume these balls underneath our feet are protons and neutrons of the uranium atom.
The protons are red and the neutrons are blue. But these are just abstractions for the sake of your imagination. The rather prosaic name we give this particular uranium atom is 92U238.
92U238? That's not a very catchy name. But what is that shimmering haze buzzing all about us off in the distance? Oh, wait a second, I know those are electrons.
Yes, very good. These are very, very small, and as you notice, also very far away comparatively. The diameter of the atom's nucleus is 10,000 times smaller than the total atom, the outer boundary of the total atom being the outermost shell of electrons whizzing about it. In between the nucleus and the electrons is just empty space. I trust that you have in your lecture notes that 99.999% of an atom is empty.
Right, of course. But, say, didn't Professor Igor also say that the nucleus would appear to be the size of a small pebble if the uranium atom was blown up to the size of a football stadium?
Football? Oh, yes, yes. I'm so sorry. It's so confusing when you Americans use the word football. English football is what you Americans call soccer, but I always preferred the grandfather of American football myself, rugby. Was quite a good forward during my days at Nelson and Canterbury, if I may be so bold.
Well, in any case, in contrast to Professor Igor's analogy, I prefer the analogy that the nucleus is like a gnat in a cathedral.
Well, that works too, but whether you compare an electron to a pebble, or a grain of sand, or even a gnat, they really do not even exist in a single location, as a pebble or a fly might. Instead, an electron has a finite possibility of existing everywhere and nowhere at the same time. When the cloud is more opaque, there's a greater possibility you'll find an electron. Where it's more transparent, a lesser probability.
One could probably use the analogy that the electron is like a hyperchild as well.
Yes. What a delightful analogy, my dear chap. Quite as well. Well, it takes about 150 attoseconds for an electron to orbit an atom's nucleus. What is an attosecond, you may ask? An attosecond is 10 to the negative 18th seconds long. Or think of it like this. 1 attosecond is to a second as 1 second is to the entire age of the universe.
Oh my god, that's fast. Even faster than a New York minute.
Indubitably. It wasn't until 2008 that scientists were able to record the first video images of an electron's orbit. The particle is so quick.
I think I may remember reading that somewhere. So, how many electrons does a uranium atom have then?
92, one for each proton. All the stable atoms, as a matter of fact, have an equal number of protons and electrons.
So that's why the uranium atom's first name is 92.
Yes, and while there are 11 elements with more protons than uranium, and thus are heavier, uranium is the largest and heaviest of all atoms, which exist naturally on Earth. But tell me, Tompkins, can you tell me how many neutrons a common uranium has, based on the fact that the uranium atom's last name, to use your analogy, is 238, with 238 being the total combined number of protons and neutrons?
Well, if you subtract 92 protons from the 238 total nucleons, you get 146. 146 neutrons.
Very good, Mr. Tompkins. I forgot that you're a bank clerk. Simple subtraction must be child's play for you.
Elementary, my dear Rutherford. Get it? Elementary. So I have a question about the gold foil scattering experiment that you and your assistants Geiger and Marsden performed in 1909.
Yes?
You shot alpha particles at various atoms in the foils you were bombarding. Did it ever happen that your alpha particle hit the nucleus and split it in half?
Mr. Tompkins, that is just an extraordinarily clever question. I haven't even yet discussed nuclear fission with you, and here you are bringing it up like an idiot savant. As a matter of fact, 20 years after the scattering experiment, I and my close colleagues Cockcroft and Walton performed an atom-splitting experiment. First, we decided we could not use the alpha particle because it had too large a mass, 2 protons and 2 neutrons, and it had too large of a charge, +2. So we used as our projectile a far lighter and less charged projectile, the nucleus of the hydrogen atom, a proton.
Couldn't you have used an electron as your projectile?
Yes, we thought of that. The voltage necessary to create fast electrons wasn't possible, so we decided on the proton. Its high mass required much less voltage at high frequencies, and we wanted to build on past experiments with positively charged particles.
I'm so sorry if I've annoyed you.
It's alright, just please, no more questions until I'm done explaining. You interrupt my flow. So, as I was saying, for the experiment, we decided to use a proton as our projectile. Under my direction, Cockcroft and Walton built a particle accelerator, which would speed up the proton to a speed fast enough that it could split the nuclei of lithium we would use as our target. Here you see me sitting in the tea crate of the accelerator, looking much more young and dashing than I really was at the time. It was quite cramped in there, I might add. The accelerator was an 8-foot glass tubing encased in a particle vacuum. From a smaller tube inside the larger one, the positively charged protons shot through 2 electrified, negatively charged metal cylinders, thus gaining energy and speed. When they left the cylinders, they struck the lithium target at the bottom of the tube. Since it is the largest known metal element on the periodic chart with 2 protons and 1 neutron, we used lithium. The majority of the accelerated protons didn't hit anything when they hit the lithium target. Only 1 of every 1,000 million protons collided smack dab into a lithium nucleus. When they did, alpha particles, helium nuclei with 2 protons in the nucleus, were created. And of all the alpha particles created from the collision, only a paltry few made it down the tube to the fluorescent screen from where the collision can be seen and photographed through a microscope. By the way, I forgot to mention an anecdote of incredible synchronicity. This was in the early days of preparing our experiment, when we were trying to solve the problem of obtaining a high enough voltage to accelerate the protons. In 1928, Niels Bohr sent a 24-year-old physics student to visit us. When we told him of our conundrum, he almost immediately gave us the correct answer, doing most of the calculations in his head. It was extraordinary. He explained the quantum theory allowed protons to act as both particles and waves, which would allow them to tunnel through the energy barrier binding them to the nucleus. Cockcroft, inspired by the young student, reversed the idea and calculated that the protons of high energy might just be able to get through the same energy barrier and enter the nucleus. Any idea of who that budding young physicist might be?
I'll bet you all the money in the world, and I've counted much of it, that the visiting student was none other than my own creator, George Gamow.
Give that man a cigar.
I suppose the fact that my creator was so intelligent explains a lot about me. But please, answer me this. If we're standing on the nucleus of a uranium atom, don't we risk getting blown to smithereens if it decides to disintegrate into another kind of uranium atom?
Well, you see, Mr. Genius, it comes down to the concept that I discovered, the half-life, which is the time it takes 1/2 of a radioactive material's atom to disintegrate. For 92U-238, the half-life is 4.5 billion years, which also just happens to be about the same age as the Earth. So the probability that our uranium atom will blow us up to smithereens in the next few minutes is extremely small.
Well, I still don't like it. If it's so unlikely to blow up, then why is it that an atomic bomb has no problem blowing up at a moment's notice?
Well, broadly speaking, it comes down to the notion that there are 2 types of nuclear chain reactions, controlled and uncontrolled. A nuclear reactor for powering things is an example of a controlled chain reaction, while the explosive release of energy in a nuclear weapon is an uncontrolled nuclear chain reaction. Controlled fission or uncontrolled fission?
Fission?
The word fission simply means splitting something into smaller parts. Thus, nuclear fission involves the splitting of an atomic nucleus into smaller nuclei. The first theoretical detailed studies trying to understand nuclear fission were made by Niels Bohr and John Wheeler. In 1939, they concluded that within the nucleus of an atom, there are 2 competing forces. All the protons in the nucleus undergo mutual repulsive forces, since they all have the same charge, positive. Counterbalancing these repulsive forces are the attractive nuclear forces. If these two forces are exactly balanced, the nucleus is quite stable. Watch and learn, my boy. Let's fire a neutron at the uranium nucleus. Since a neutron is electrically neutral, it won't get repelled by the positive uranium nucleus. And when the uranium nucleus absorbs this neutron bullet, it becomes unstable. The reaction, or fission, splits the uranium nucleus and creates two new elements, barium and krypton. On December 2, 1942, Enrico Fermi, an Italian physicist working in the United States, secretly did the first controlled nuclear reaction under the grandstand of Sprague Field, the University of Chicago Stadium, a field where, incidentally, many American football games were played. Though it was a crude pile of black bricks and wooden timbers, as Fermi himself said, Chicago Pile 1 was the world's first man-made nuclear reactor.
How was Chicago Pile 1 constructed?
Good question, Mr. Tompkins. The wood provided scaffolding for a lattice of over 12,000 pounds of pure uranium metal and another 84,000 pounds of powdered uranium oxide. Stacks of black graphite bricks, 2/3 of which were embedded with pseudospheres of uranium containing both U-235 and U-238, were used for slowing the neutrons down to a speed more conducive to fission. As the neutrons shoot through the brick, they collide against the carbon atoms in the graphite, which act rather like sandbags do for bullets on a firing range. U-235 is more fissionable than U-238. The effect, as we have seen, is that with a huge release of energy, U-235 splits into the daughter elements barium and krypton, with additional fast, footloose, and fancy-free neutrons which careen into other U-235 atoms, splitting them and continuing the chain reaction. To prevent an uncontrolled fission chain reaction occurring within the pile, Fermi and his team inserted cadmium rods into it to absorb the free neutrons.
If all these U-235 atoms are blowing up, why is it that Fermi didn't blow up the stadium by inadvertently creating an atomic bomb?
Mr. Tompkins, you're smarter than you look. Good question. The answer is that in natural uranium, there's only 7% of U-235, and 93% is non-reactive U-238. The fission process is therefore too inefficient to convert into a nuclear bomb, or even into a nuclear power plant. Fermi only got half a watt of power, but Chicago Pile 1 did give us a glimpse of the future, nuclear bombs and nuclear power plants using custom-made uranium atoms.
So why are U-235 and U-238 so very different in behavior since they're almost identical?
We really do not know why the minority of uranium atoms have 143 neutrons and why the majority have 146. They just do. One of the mysteries of the universe, I suppose. However, we do know that the ratio of neutrons and protons in the nucleus is critically important and that the stability of the atom is the determinant factor. The strong nuclear force attracts protons to neutrons without repulsing other neutrons. The more neutrons attracted, the more stable the uranium nucleus, and conversely, the fewer neutrons, the less stable the nucleus, and the more fissionable. So since it has 3 fewer neutrons in its nucleus, U-235 is lighter, less stable, and thus more fissionable than U-238, and even more fissionable with the slow neutrons than the fast ones. It was really quite confusing when this fact was first discovered.
I'm still confused.
Mr. Tompkins, I think our uranium nucleus we are standing on is going to disintegrate.
But you said... Where am I? If only all my dreams were so interesting. Boy, does time fly. I gotta go to work.